Okay, so this talk is going to be about private information retrieval, or PIR, which is a very powerful, very useful, but also very expensive cryptographic protocol, and what we can do to make it more efficient in practice. So if you're not familiar with PIR, here's the basic setup. There is a server, and this server has many files. These files could be movies, they could be songs, they could be academic papers, it doesn't matter. There's also a client who wants to access one of these files, but it doesn't want to reveal which of these files it is accessing to the server. One way in which the client can do this is the client can just download the entire database and then locally select the file that he or she cares about. But this has very high communication costs. So the purpose of PIR protocols is to achieve this privacy guarantee, but at a much lower communication cost. And like I said, PIR is very useful and it has many applications. For example, if you want to figure out which of your friends are part of a social network, but you don't want to reveal to the social network operator who your friends are, you might use PIR for that. If you want to fetch ads without revealing which ad you fetch from the ad network, you might use PIR for that. If you want to watch a movie on Netflix, but you don't want to reveal to Netflix which movie you're watching, you might use PIR for that. So you get sort of the point here. PIR comes in two flavors. One of them is the information theoretic flavor. This requires multiple servers that do not collude with each other. So if you're okay with that assumption, then you can use that. There's also the computational variant of PIR, which requires cryptographic assumptions and is more expensive, but it doesn't require the non-collusion assumption. So personally, I prefer this because it's much easier to deploy because you don't have to make that assumption. And so that's why I'm going to focus on this. So just to give you our results in a nutshell, here the y-axis is the amount of communication required between the client and the server to fetch a single file from a database. Here the x-axis is the size of the database, and the black line is just downloading the entire database. And the yellow line is just a non-private retrieval. Basically, you ask the server, please send me a file, and the server sends you the file. The orange line is XPIR, which is the state-of-the-art computational PIR library. And if you take a look at what it costs to download a 288 byte file, it's actually pretty significant. It's 17 megabytes. That's 60,000 times more costly than the non-private version. Our work improves this by an order of magnitude or so. And I'm going to describe how we do it. So we basically are able to do PIR on larger databases or use PIR on regimes where network communication is not plentiful. For example, if the clients are mobile devices. Okay? So the rest of this talk is going to be as follows. I'm going to give you some background on a concrete PIR scheme. Then I'll tell you what the sources of overhead for that PIR scheme are and how our solution addresses them. And then I'll talk about our implementation and evaluation. So let me talk about the PIR protocol due to Julian Stern, which was proposed in HOCrypt in 1998. So in PIR, there's this underlying assumption that the client knows the exact position in the server's database of the element that will be retrieved. So in this case, the client is interested in file 2. So it knows that the file is at position 2. What the client does with this information is it generates a query vector where every entry in this vector is a 0, except for the entry at position 2, which is a 1. Now, what the client does is it then encrypts each of these entries individually. The way to interpret this is that each blue box is an encryption, as a different encryption of 0 and encryption of 1. This is semantically secure, so they're all indistinguishable from each other. And this is also additively homomorphic, meaning that the server, without having the secret key, can take two ciphertexts and add them and then get back the sum of the corresponding plaintext. And it can also multiply a ciphertext by a plaintext. So what the client does is it sends this query vector over the network to the server, and the server computes a dot product. So this is going to be a bunch of entry-wise multiplications. These multiplications are between ciphertext, the blue boxes, and plaintext. You can think of files as giant integers. And then multiplying by 0 gives you 0, and multiplying by 1 gives you whatever you started with. And then because each of the ciphertext, because the encryption scheme is additively homomorphic, the server can add all of the ciphertext in the output into a single ciphertext that encrypts the file. And this is what the client sends back to the server, what the server sends back to the client. Now, you might look at this and say, well, hold on one second. The size of the query vector is as large as the database, so how are we saving any communication at all? Well, there's a standard technique to reduce communication costs, which is that if instead of representing the database as a vector, we represent it as a matrix, then we just need two queries, one to specify the row, one to specify the column, and observe that each of these query vectors are square root of n, and therefore the communication is going to be sublinear in n. Okay, so this is Stern's protocol, and one of the issues with this protocol is that even though the communication is sublinear, we're still sending thousands of ciphertexts between the client and the server. So in other words, the query is still very large. The second issue is that the computation that the server is performing, all those homomorphic operations, are very expensive. So in the paper, we discussed two techniques. One is a compression technique that allows us to take this entire query vector and make it into a single ciphertext that the client can then send to the server and in turn save communication cost. We also have an encoding that allows the server to encode the database in such a way that it can process a batch of queries from the same client, and that processing is more efficient than processing each query individually. In other words, the server gets amortization. If you're familiar with batch codes, our encoding is a relaxation of batch codes, but is weaker, but it's much more efficient. So in this talk, I'm only going to focus on how we do compression. If you're interested in how we do the encoding, please take a look at the paper. So abstractly, what we want is for the client to, instead of sending this gigantic query vector, to just send an encryption of 2 to the server. But why doesn't this work right now? The reason it doesn't work is because the PIR protocol that I showed you earlier requires this query vector of zeros and ones so that you can do the dot product. Okay? So what we're going to propose is for the server to compute a decompression function on this encryption of 2, and the output of this decompression function should be the query vector that the client would have generated in the first place, and the server should be able to do this without learning anything in the process. So one strawman solution to do this is, let's just use fully homomorphic encryption. So if we have the ability to add ciphertext and multiply ciphertext, we can compute arbitrary functions, including decompression. The problem with using fully homomorphic encryption is that multiplications are very, very, very expensive. They're orders of magnitude more expensive than some of the other operations. But what's worse is that if you're going to use multiplications, you also have to use larger security parameters, which means that some of your other operations become more expensive as well, which means that the entire PIR protocol becomes more expensive. So our goal is to implement this decompression function without using any multiplications at all. Now, to explain how we do this, let me first present XPIR. So XPIR essentially implements Stern's protocol, but it makes one key optimization, which is that instead of having this ciphertext be, for example, the PAL-E crypto system, they're going to be from a lattice-based crypto system. And you're going to pre-process the database, and the result is that all the homomorphic operations are going to be much more efficient. So in XPIR, the plaintext space, they're not integers, they're actually polynomials. So 0 is just going to be represented as the polynomial with all 0 coefficients. And 1 is going to be represented as the polynomial where the constant term is a 1 and all of the other coefficients are 0. Furthermore, because the plaintext space is polynomials, all of the files also have to be encoded as polynomials. And this encoding is very simple. Just take the first 20 bits of the file, put them in the first coefficient, the next 20 bits in the next coefficient, and so on. Okay? Now, what we observe is that this lattice-based crypto systems support an operation called substitution. This is an operation that was used by Gentry, Halevy, and Smart to build arbitrary permutation networks, but we don't need all that generality. We just need the substitution building block. And what substitution does is, given an encryption of a polynomial, and so integer, let's say 3, it allows you to get back an encryption of a polynomial where every instance of x is substituted by x cubed. Okay? And this operation is orders of magnitude more efficient than homomorphic multiplications. And we can use these 3 operations, addition of ciphertext, plaintext ciphertext multiplication, and substitution, to build a function called extract. And here's how extract works. So for extract, we start with an encryption of a polynomial. And what it allows you to do is it allows you to take each of the coefficients and place them in the constant term of a new encrypted polynomial. So for example, we take the 0, and we place it in the constant term of a new polynomial. We take the 2, we place it in the constant term of a new encrypted polynomial. We take the 0, place it in the constant term, 0, place it in the constant term. Then we can use this extract procedure to build the compression and decompression as follows. So in XPIR, what the client is doing is generating a bunch of different encryptions of 0 and an encryption of 1. What we're going to do instead is encode this query vector in the coefficients of the polynomial. So because the client was interested in the element at position 2, we're going to set the 1 next to x squared, and everything else, all the other coefficients are going to be 0. So this is going to be a single ciphertext of this polynomial, which the client is going to send to the server. Now the server is going to receive the ciphertext, and what it will do is it will call extract on it. And if you notice, by extracting all of these coefficients, the server was able to reconstruct the query vector that the client would have generated in the first place. And then the server can proceed with the rest of the PIR protocol as before. Now you might look at this and say, hold on one second, what is the degree of this polynomial going to be? Is it going to be as large as the database? And the answer is yes, but recall that previously we are structuring the database not as a vector, but as a matrix. So really the degree of the polynomial is going to be square root of n, or if we want it to be smaller, we can go into higher dimensions. We can represent the database as a d-dimensional hypercube. Okay? So in other words, we've managed to instantiate this abstract solution where the client is sending this encryption of 2, and the server is performing this decompression on this encryption of 2, getting back the query vector, doing the rest of the PIR protocol. Now, let me talk about our implementation and evaluation and hope to convince you that this is actually efficient. So we've implemented 2 libraries. One is called sealPIR, which is essentially XPIR, but with the decompression procedure. It's a different code base for reasons that we explain in the paper, but it's not fundamental. We also have a library called MPIR, and this library allows the server to encode the database to process multiple queries more efficiently than processing each query individually. And then we also re-implemented the Pong private communication system using both of these libraries to see what are the kinds of benefits that you can expect to see from using our techniques. So in the paper, we answered 3 evaluation questions. The first is, does compression reduce network cost, and what is the overhead of decompression? The second is, does batching work well in practice? The reason I say work well in practice is because our batching scheme is probabilistic, meaning that if the client wants to get, say, 20 elements from the database, sometimes it might only be able to get 19 or 18 or 15. And so we wanted to quantify how often do queries fail and whether that's acceptable in practice. And in the paper we do that evaluation, it comes out to like 1 in a billion queries fail or something along those lines. Now, we also evaluated the Pong system and we saw significant improvements. So in this talk, I'm going to focus primarily on on the cost of compression and decompression. So here I have a comparison with XPIR. This is the cost of running a single PIR query on a database with 1 million entries. Each entry is 288 bytes. And what we find is that compression significantly reduces the cost, the network cost, the size of the query by up to 2 orders of magnitude. And this has a second benefit, which is that it also reduces the computational cost to the client to generate the query. This is because in XPIR, the client is generating a bunch of encryptions of 0 and 1, whereas in sealPIR, the client is only generating a polynomial and then encrypting that polynomial. This is much more efficient. This does come at a cost, specifically a cost to the server, because the server has to perform this decompression function. But what we find is that the overhead is pretty small. It's about 6%, which given the significant savings that we get in network cost reduction, I think this is an excellent trade-off. Okay. Now, a lot of times I've received feedback that if you only care about performance and not network resources, then you're better off just downloading the database. And this is true, but only if you have very high network speed. So the graph on the left, SCP is the secure copy command line tool. So this is basically downloading all of the database. And what we see is that, indeed, if you have a lot of network bandwidth and you only care about performance, you're better off downloading the entire database. However, if you have network conditions, for example, the kinds that you would see on a network device, it's actually much more beneficial to, even if you don't care about the network consumption, it's more beneficial to use sealPIR just for round-trip time reduction. Okay. So just to summarize, in our paper, we have 2 techniques, one to compress PIR queries so that they're smaller and you can save network resources, and another one to amortize the computational cost of processing a batch of queries from the same client. We actually get 56 times reduction in network costs with compression and up to 40 times reduction with batching. One of the things that gets me excited about these improvements is that the client costs are actually low enough that you can envision using PIR in mobile devices, both in terms of computational costs, but also in terms of network costs. And we find that when we apply both of these techniques to the Pong private communication system, we can simultaneously achieve higher throughput and also lower network resources. With this, I conclude my talk, and I'm happy to take any questions.
Hi, I have two questions.
Mm-hmm.
So first, in terms of the batching, are you using cuckoo hashing? Is your failure probability related to the fact that we don't know how to limit the stash, or am I off?
There is no, we're using cuckoo hashing, but with no stash. And so the failure probability is computed empirically, we don't have a boundary.
So how come without stash?
Yes, so we don't have a stash, which means that if you cannot map, if there's at any point any collision into the same bucket, that means you can only get one of the elements, yes.
Okay. And my other question was, so how hard is to get to symmetric PIR from your implementation? Is it inherently your client is getting more than the one item that is desiring in your construction?
Yes, because so for example, in Pong is a private communication system that allows you to have group communication. And in group communication, you want to send a message and then get multiple messages at the same time. So we were looking for that particular scenario.
Okay.
You can, for seal PIR, if you're not worrying about batching, you might be able to get it to be symmetric.
Okay, thanks.
Yeah. Any other questions?
So I'll ask one. So that the overall server processing time, I think that what you add with the decompression is not a concern, but the high overall cost that seems intrinsic with this style of PR scheme, is there any hope for reducing that?
So yes, the computational cost of answering a PIR query is going to be linear in the size of the database. And I don't know of a way to make it not so. But one of the things that's exciting about this particular protocol is that it's easy to parallelize, because the dot product, you can compute it on different cores. So you can definitely throw hardware at the problem.
Okay.
Is there time?
There is, yes. I can see you. Yes.
My question is, has anybody evaluated just FHE? It seems like there you could have a log size ciphertext. You'd have, of course, log depth multiplication, but it's not clear to me that that's going to be so much worse. Is there a paper that does that?
So no, there is no paper that has actually implemented it. But Brakarsky and Vaikuntanathan propose essentially what you're saying, where you're just sending the encryption of 2, and then they evaluate this on the entire database.
It goes back even further. I mean, I think even Gentry does that in his thesis. So.
Yeah. But I think it will be much more expensive, and the reason is that substitution itself is orders of magnitude more efficient than a single multiplication, and we only need to use order degree multiplications. So in what you're proposing, you're going to require n log n multiplication. So that's already going to be like significantly more expensive for decompression.
But communication will be smaller.
Yes, absolutely.
So it's not clear that one scheme is going to be certainly better, right?
Well, I mean, if your communication, we're already at 300 kilobytes. So if your communication is going to bring it down to, say, 10 kilobytes, but it's going to take you 5 hours to process a PIR query, then it's probably not a good trade-off.
Okay, let's thank Sebastian again.